In this example, we're given a circuit that had the switch connected to this point for a very long time, and at time t equals 0, we just open that particular circuit and we'll end up with this part. And in this part, of course, the capacitor beforehand was being charged with the 30 volts source. And after that, what we will do, it will we'll have a natural response in here, or basically give that energy to the 15 kilo ohms and the 25 kilo ohms. And what we're being asked to compute is the voltage across this capacitor after time equals 0, and this particular Vx, which is just the voltage across the 25 kilo ohms, given that this is negative and this is positive in here. So what I will do is in here is I'll just basically write the equations. Well, we know that this is natural response, so based on the natural response equation, this is what we have. So Vt across that particular capacitor is just simply the initial voltage across it, and then we have to compute the R of C. And of course, if we are interested in the current flowing through it, this is what we need to do. But we're not at this point, but we're interested in that. Okay, so what we need to do is we need to figure out what V0 is and what RC is. So let's try to figure out what V0 is. Well, V0 is the initial voltage across that capacitor, and we typically compute it right before switching. So before switching, what we had is we have this particular circuit, which is 30 volts connected to an 80 kilo ohms in here. Okay, so this is 80 kilo ohms, and then it's also connected to this 40 kilo ohms in here. Okay, and the switch was closed, so basically this one here and this one here is closed, and we have 15 kilo ohms and another 25 kilo ohms in here. So this is 15 kilo ohms and this is 25 kilo ohms in here. And of course, the capacitor at this particular point acts as an open circuit, so all we have to do is just basically say that this between here and here, that will be the V0. Okay, so the voltage, the initial voltage across that capacitor in here, or we can also call it Vc at exactly 0. Okay, or before 0 if you wanted, but let's assume that this is basically the initial voltage. So our task is just to figure out what this voltage V0 is, and this is pretty straightforward circuit, so there's multiple ways to do it. You can tell me, well, let's combine these two resistors in series, so we know that 15 and 25 is simply 40, and those two will be connected to another 40 here in parallel. Well, 40 and 40 in parallel will actually result in 20, so what the circuit that I have in front of me should have basically a 30 volt in here, okay, connected to an 80 kilo ohms in here, and then another, basically from here to here is just simply 20 kilo ohms. And of course, the voltage that I'm interested in is still the same voltage between here and here. That's plus minus, and we called it V0. It's the same voltage because it's a voltage across the 15 and 25. It's a voltage across the 40. It's a voltage across that 20 kilo ohm that we have in here. And we can simply compute this as V0 is just simply 30 volts times 20 divided by 20 plus 80. Okay, 20 plus 80 is 100. So that should probably be around 6 volts. Or exactly 6 volts. That's what we have. Okay, so that will be 6 volts. So we were able to figure out the V0 for now. So we figured out this particular part. So let's figure out what the RC is. Well, RC, actually, we have to look okay, so the V0, what we do is we look at the capacitor right before switching. But for the RC, what we do is we'll look at the voltage, or we look at the circuit right after switching. So right after switching, what we will have is we have this resistor and another resistor in here connected to this capacitor in here. That's what we have. Okay, let me just change the color back to blue in here. Okay, all right, there you go. So what we have is we have a 15 kilo ohms and we have 25 kilo ohms. And we have the C in here, which happened to be 5 microfarads. 5 microfarads, that's basically the C in here. And that's, of course, from here to here is Vc of t. That's what we're looking for. All right, and eventually we'll figure out with negative plus, that will be Vx of t. Okay, so what happens is, like, which one is the RC? Because tau, the one that we're trying to figure out now, tau is just simply RC. So which R? You shouldn't be just picking up a random R. There should be only one R. This is natural response of an RC circuit, so there should be one C and one R. So what we need to do is we need to combine these two. So the most common mistake I've seen is students just basically pick up 15 or 25 and just substitute in here. That shouldn't be the case. What you should be doing is you combine it to one resistor and one capacitor. And that capacitor happens still to be 5 microfarads. And again, if you have like multiple capacitors, you just have to combine them into using series parallel combinations of capacitors. This one here should be basically 40 kilo ohms. And now that's what we have in here. So the RC, the tau, is just simply 40 kilo ohms. So we have to multiply by 10 to the power 3 to convert it to ohms, times 5 times 10 to the negative 6. And that will give me 0.2, or just simply 1 divided by 5. And that actually has a unit of seconds. And of course, because we're going to be using 1 divided by RC equals 1 divided by tau, I usually just go ahead and compute it, which is just simply 5. That's what we will have. Okay, or 5 second minus 1. That's the unit because the reciprocal of tau. All right, I think now we have everything we need. So the VC in here, the one in here, we can just use this particular equation right away. So let me just highlight it in here or just copy it. Okay, so we're going to copy this here, and we can just substitute now with the values that we need. Okay, so we don't need this here. Okay, so what is the VC of t? Well, simply V0. What was the V0? Well, we computed that to be 6 volts. E to the negative t times, well, 5 of t, and that's for t is greater than or equal to 0. Remember, the equality is fine because before and right after 0, the capacitor's voltage does not change, and that's pretty much it. And of course, if you think about it, if you wait, just a sanity check, if we wait for infinity time or 5 taus, okay, this will go to 0 and the capacitor voltage will go to 0, which makes sense. There are no sources in this particular circuit, so that's it. Now, what else are we interested in? Well, technically you can compute with the current if you're interested in the current, and you can go ahead and just compute what the current is. And you can do it 2 ways. You can either take this equation here and tell me, well, this is how the current is computed, or you can just basically take CdV divided by dt, basically. Okay, so you can just basically tell me, well, this is here. If you're interested in the current, simply you can tell me I C of t, and that's basically the current flowing through that way, I C of t. Okay, that's how the current is flowing. This is I C of t. Okay, and let me just make sure I highlight it, the direction of it, I C of t. Okay, it's basically going from, well, out of the positive. That's what we have. Okay, so I C of t is just simply V0, which is 6 divided by R, and this R in here is a 40 kilo ohms. Okay, so if you use 40, you will, and it's 40K, so it will get the result in milliamp, e to the negative 5 of t, and that should be equal to, simply, let me just write it in here, 0.15 e to the negative 5 of t milliamp. Okay, and that's for t is greater than 0, not greater than or equal to, because the current before was 0. So if you think about it, at IC 0 we can't have a 0 because actually at 0 there will be a jump. At 0 minus it was 0 volts, because if you think about it, in this particular case in here, this is 0 minus in here, this is 0 minus, there's no current flowing through that capacitor. But right after switching, what we end up with is the following in here, and there will be a capacitor, there will be a current flowing. So we will have IC0 plus will simply be 0.15 milliamp. All I did is substituted the 0 in here in this particular t, and of course this goes to 1, so that's 0.5 milliamp. Okay, so that is why we say this is t is greater than 0, not greater than or equal to 0. All right, so we're not done, because what the question is asking me to do is just to figure out what Vx is here. So what I have to do is I have to take a look. Well, I know the equation for Vc of t. What I'm interested in is this particular voltage in here. Well, I can just simply use voltage division on the equation. So what I have is I'm interested in V of x. Let me just write this equation in here, or maybe I'll just copy this. Okay, we'll copy this, and what we're interested in is the following. So I'm interested in V of x. Let me just write it in here. So V of x of t is just simply negative Vc of t times 25 divided by 25 plus 15. That's just basically basic voltage division. It just happened to be now the voltage in here is a function of time instead of being just 5 volts or 6 volts or whatever it is. Okay, so all we have to do is just substitute. So we substitute, what we will end up with is the following, and the negative sign is just because this is positive, this is negative. I'm looking for the negative positive in here. That's why we have negative. Okay, so we get negative in here. So negative Vc of t, which is basically this equation, which is 6 times e to the negative 5t, I believe, times 5 divided by 8. Okay, so let me just do a little bit of multiplication here, and I will end up with negative 3.75 e to the negative 5t. And that's exactly, in this particular case, is greater than or equal to 0. And the reason why it's not exactly greater than, I mean, typically it will be greater, exactly t is greater than 0, is because this particular voltage, if you actually go all the way here, you'll see that right before switching, basically, it was still like V0 divided between the 15 and 25, and right after switching, it's the same voltage because of the way this circuit is built. So that's pretty much it, and that here is, the unit is actually just simply volts. That's what Vx of t is.